All right, let's try that again. All right, cool. So, exams are coming up. Your first exam for your first lecture exam will be on Monday. If you guys want to show up, you'll want a Scantron.
On Monday?
Yes, bring a Scantron with you.
Monday or Tuesday?
Tuesday, sorry.
Okay.
Yeah, sorry. I know I'm starting another class on Monday, so yeah, Tuesday. Yeah, you guys show up Tuesday. Scantron, please. 50 front, 50 back, and I'll talk about that exam in more detail.
Is that the green one or the blue one?
Oh, I think it's green. Yeah, it's a narrow. Yeah, 50 front, 50 back. I'll talk about that in a little more detail, though. I'll get through the lecture today first, which should go fairly quickly because a lot of this is just a recap from the lab that you did. There are a few new things that have been thrown in, but by and large, it'll be a pretty good review. Okay, so I went through the quiz. I know there are a lot of people a little anxious about their grade. Sorry, I don't know what to tell you. I was very, very unambiguous about when the quiz was due. I wrote it all over the all over the lab. I stated it. I put an announcement in Canvas. The quiz itself had a due date and time on it. I don't know what what additional information I could have done to be more unambiguous about that. But on the good side, it's only 20 points, right? So it's not now. A lot of people are really worried about their grades. The reason that impacted your grade was so much is you don't have a whole lot of points yet, right? You have a few labs, and that's about it. You have a few labs and then a 20-point quiz from a couple weeks ago. Those are all the points. So the more points you accrue, the less 20 points is going to impact that grade. Does that make sense? What really will impact your grade is this first exam coming up on March 1st, I think it's March 1st, on Tuesday. That's 100 points, that's 10% of your total grade there, so definitely want to make those tests count. I will do something a little interesting, though, because sometimes people can struggle a little bit. Maybe they don't study or they kind of underestimate the difficulty and don't apply themselves as much, and so they may struggle on the first exam. And so what I will offer to everybody is what you may be able to do, or what you will be able to do is, let's say that you scored a 50% on your first exam, okay, and you just feel terrible, like, oh geez, this isn't good. As an incentive to keep at it, to keep studying, to get through the course, what I'll do is when you take your final exam, I will give you the option of exchanging the grade that you get on your final exam for one of your other exams. So let's say that you got an 80% on your final exam, and you got a 50% on exam 1. You keep your 80% on the final exam, but I'll also give you that on your exam 1, say. Does that make sense?
Oh, yeah.
So you do have that option. So that kind of gives you, if you really mess up or something, it kind of gives you if you do well in the final, then that kind of gives you, enables you to kind of get it on the rebound, if you will.
Will the final exam be just like on the last chapters we do, or like
It's a comprehensive. Final exam is comprehensive, yeah. So it'll be over everything. Yeah. So all the lecture exams are a certain number of chapters, and it specifically states in the syllabus which ones. Your first one is chapter 1 through 6. And like I said, I'll do a review after I get through today's, because this is actually chapter 6, and so some of this material will be on your exam. But so you guys okay with that? Does that kind of make sense? Yes. What you got? Well, I'll talk about that. Like I said, I don't want to do an exam review right now because we have lecture material we need to get through. But at the end of class, I'll talk about that in a little more detail. And then you have your lab exam on the 10th, which is another 10% of your grade. So March is going to basically be a pretty big month. I believe you have 2 lecture exams and at least 1 lab exam. So basically 30-40% of your total grade is going to be in March, if you want to think of it that way. So a lot of stuff there. So definitely incentive to keep studying. Like I said, I'm here early, pretty much every day, about an hour or so before classes start. So I'm always available for to go over additional concepts if you need. And as we continue, there will be additional quizzes that'll come up as well. And I'll always do a quiz review prior to lecture, after the day after, the week after you guys take that. Okay, so let's go ahead and get started. Any questions so far? Are you guys good so far? All right. We'll get through the major material we need to today, and then we'll talk about the exam coming up next week. Okay, so let's go ahead and just review the basically chapter 6 is an introduction to support and movement, talking about osseous tissues and general bone structure. So the good news is you're not going to have to know a whole lot of specifics. Okay, you're not going to be memorizing every single bone in the body, okay, for this first exam, so that takes some of the pressure off. Okay, it's going to be a bit more broad. But let's just talk about the general functions. There are 5 primary functions of osseous tissue, right? It provides support, right? You can hang stuff off of your bones, right? Muscles, soft tissues. You can hang stuff off those bones, and your bones are really good at supporting other tissues. Bones are also good for storage, specifically of lipids and minerals, different minerals, calcium being one of the biggest ones, right? Phosphate is another important one as well. And in fact, your yellow marrow is composed primarily of what? Fat, yeah, it's lipids, yeah, absolutely. Not red blood cell, but blood cell production in general, both red and white blood cells. And those stem cells, or those progenitor cells, exist primarily in red marrow. Okay, so red marrow versus yellow marrow offers protection, right? Most of our vital organs are protected to some degree by our skeletal system. The most vital organs are protected even more. For example, the brain, right? The brain is encased entirely in bone, whereas another organ like your heart is not cased entirely by bone, but it sits in the center of your rib cage and is protected by your sternum and multiple ribs. And then other organs are less protected, such as your intestines, by and large, are not protected by bones, right? So in general, the more vital the organ, the more kind of protection you have, right? Your lungs and your heart have a pretty good amount of protection. Your brain has an exquisite amount of protection. Your spinal cord is very well protected as well. And then bones are also good at giving us leverage, right? So we can move stuff, we can slide stuff, we can pull stuff, and it gives us leverage to articulate or to move. Okay, so those are the major functions. Seems pretty easy. Okay, let's just quickly review the different shapes. Okay, and we talked about these in lab, but we have what are called long bones, right? And these, it's not the actual length that we use, right? We talked about this in lab. It's not that a bone is long that makes it a long bone. What makes a long bone a long bone? There you go. It's longer than it is wide. Right? So throw some major examples of long bones out at me that we talked about in lab already. Okay, the femur, yeah.
Humerus.
Okay, the humerus. What else? So you got the femur, you've got the humerus.
Tibia.
The tibia and the fibula go together, right? Those are in the lower leg, right? The tibia and the fibula. And then you have your 2 long bones in your forearm, the
Radius.
right, the ulna here and the radius here. So you got the radius and the ulna. Good. Radius, ulna. And then also, right, you have right? Your phalanges, okay, are long bones, right? But the other type of bone, short bones, are, what makes a short bone a short bone?
Just as long as it is wide.
It's approximately as long as it is wide. And where do we have short bones? What are some major areas of the body? The wrist, right? So the bones right in here. You've got your wrist, and then your ankles as well. You have lots of little short bones in there. Absolutely. Okay, flat bones are generally what? Generally kind of flat. What are some examples of flat bones? Sternum is a good one, right?
Ribs.
Sternum, ribs, absolutely.
Scapula.
The scapula, where's the scapula?
Shoulders.
Okay, yeah, it does form part of the shoulder. Is it anterior or posterior? Posterior, right? And then what else? What's this bone right up here? The clavicle or the clavicular bones as well. All right, good. So the clavicles. Sutural bones. This is kind of a special case here. Okay, where are sutural bones located? Yeah, in between the sutures, right, that hold the flat bones, and we didn't talk about that, but you do have flat bones in your cranium as well, right? In your head, there are some flat bones. All right. And sutural bones are bones in between those sutural lines, right? So they may be very small. Occasionally, in certain diseases, they may be larger. Okay. Irregular bones. What are some examples of irregular bones? Your vertebrae are going to be your classic. Okay.
Mandible.
Huh?
Mandible.
The mandible. Good. Okay. Huh?
The pelvic.
The pelvic? Is that an irregular bone? What do you think? Okay. Pelvic. What are these called? The cheekbones? The zygomatic bones. Good, good. And then there's a little bone here, right? A little bone here that connects some of the soft tissues of your neck, your epiglottis. It kind of sticks out. I know several of you asked me about that in lab too. What is that little bone sticking out there?
Yeah.
Starts
It's
with
that
a-
little flap.
Yeah, the epiglottis is there, some of the soft tissues attached to it. It allows us to swallow.
Yeah.
The
I don't remember the name.
hyoid bone, there as well, is a kind of irregular bone. And then sesamoid bones, what's classic? Don't give me the example, but what is a sesamoid bone? What makes it a sesamoid bone? They're not. It's not what they're connected to. It's what they're surrounded by. So sesamoid bone is fully encapsulated by what? What kind of tissue? Not cartilage. It's completely encased within either muscle or tendon, right? And where is the classic example in the human body where we have that? The patella or your kneecap is a classic example of a sesamoid bone. It is completely encapsulated by the tendon, the patellar tendon that goes across there. All right. So these are the different shapes. Okay. And I'll come back and I'll talk about some of the bone markings and some of the terminology that we use. But I kind of want to get through more of the review stuff first, and then we'll go on to the newer stuff. Okay. So how are bones formed? Okay. Well, when we're really, really young, okay, when we're really born, as we're even developing in utero, okay, before we're born, okay, your bones are very cartilaginous, right? They have a lot of cartilage. And what happens is over time that cartilage becomes replaced by proper bone tissue in a process known as ossification, okay? So the cartilage becomes more ossified over time. And so what we see is very young children have a lot more cartilage in their body, right? And so their bones are much more flexible, bendy, and pliable. And then as you transition through puberty and you become adult, your bones become hardened and they become ossified. Now, ossification means bone or osseous formation, okay? Ossification is not the same thing as calcification. Calcification is one of the things that happens during ossification, but ossification is the big, broad process, okay? And then under the umbrella of that, you have calcification, right? This occurs during ossification, and this is where you have the calcium hydroxyapatite being produced, and you have the calcium crystals that make up the matrix of the bone, right? Okay, so it starts out as hyaline cartilage, okay? And you have two different types of ossification. You have your classic type, your endochondrial ossification, and this is where you have that cartilage that gets replaced. But you can also have intramembranous ossification, okay, where you have mesenchyme, okay, the embryonic tissue that actually comes in and becomes, it transforms into osseous tissue as well. The classic thing that we talk about, and there's a classic example in your textbook, it's actually a picture, is a really nice progression where it starts out as cartilage, and that's in your developing, your neonate in utero as it develops. And then what happens is the cartilage, the cells that produce that cartilage kind of migrate away to the ends of the bone, right, to the epiphyseal parts of the bone. And then you start having the osseous tissue that develops, and it develops the hard bone first on the outside, and you can see that in the picture there, right? And then it develops further and further and further and kind of comes in, and eventually, right, the epiphyseal plate, the growth plates fuse, right? And they kind of harden up, and they become the epiphyseal lines, which you see in your more adult patients. And then you don't no longer have this active ossification occurring, okay? But with that in mind, okay, are your bones still changing in response to the environment even after you've gone through the adult transformation? Yes, right? That's something known as remodeling. Okay, your bones are changing, they remodel. And we'll talk about remodeling because there is a very strong endocrine component to that. Hormones are very important when it comes to that bone remodeling. But we'll talk about that in a little bit. Okay, so let's just briefly talk, we already did this in the lab, so I won't spend a whole lot of time, but here's just our generic picture. You probably have some better pictures in your textbook as well, and we did this in lab. But you have two general types of bone. You have your compact bone, right? And you have your spongy bone. Right? Your compact bone, okay, is the hardened, solid bone that has this classic structure, right? The basic structural unit is going to be the osteon, right? And the osteon is a central canal with several concentric rings, or we call concentric lamellae, around that. And then embedded in those rings, within lacunae in those rings, you have the cells, the bone cells themselves, right, the osteocytes. And then you have these little hair-like projections that come out of those, of where the cells are, the lacunae, right? And those are known as the canalici, right? And they allow for communication, exchange of nutrients, hormones, etc., okay? Each osteon is supplied by blood, okay? Blood flow in a venule and an arterial, okay? And ultimately, where does the blood supply for the bone come from? Well, it comes from out here, right? In the periosteum, right? And you have an artery and a vein. Okay, and the artery and the vein penetrate into the bone through what's known as a perforating canal or a Volkmann's canal, right? Perforate in, and then they branch out into the central canals. You guys okay with that? Pretty much what we talked about, okay, in lab already. All right. And then anywhere where you have internal structures, such as the trabeculae of the spongy bone, okay, it's this very porous, very porous construction here, or where you have canals, you have something called endosteum that lines those surfaces, the internal surfaces. Now, endosteum is not a complete cell layer, okay? It is an incomplete cell layer in that there are different types of cells embedded in that layer, okay? And the three major types that you want to be aware of are the osteoprogenitor cells, okay, and these are kind of the stem cells, osteoclasts and osteoblasts, okay? What's the difference between an osteoclast and an osteoblast? What do osteoblasts do? Creating what? The matrix, yeah, the bone matrix, yeah. So I think of an osteoblast as a builder, right? They are the builders. What do osteoclasts do? No. They secrete enzymes that breaks bone down, or they break bone down. So blasts build and clasts break. Yeah. Osteocytes are the mature osteoblasts. Okay, you guys okay with that? That makes sense? And we'll talk about this osteoclast versus osteoblast because it is a balance between these two that is very important when it comes to bone remodeling and when it comes to maintaining adequate levels of calcium in your blood plasma, or we call your blood serum. Okay, you guys good with that? Okay. So the blood supply enters the bone. There are three general areas. You have your diaphysis. Where's your diaphysis? We're talking long bone. What's the diaphysis? That's the shaft, right? The shaft that has the compact bone and then has in the center of its hollow, it has a medullary cavity. You have yellow marrow generally within that medullary cavity, all right? And then you also have blood supply that can enter around the area of the epiphyseal plate or the metaphysis. Right? And the metaphysis is just kind of where the epiphysis is attached to the diaphysis. It's a real difficult to locate kind of area. So you're not going to know. You're not going to have to identify exactly where that is, but that's just what it is. All right. So it's more or less the same area. I just kind of grouped those together. So you basically have blood vessels that enter the bone along in the diaphysis and then along the epiphyseal area on each end of the bone. You guys okay with that? So far, so good? All right. Pretty much review. All right. Well, let's go ahead and move on then and talk about bone remodeling. Okay? So your bones respond to stress. All right. Running, weightlifting, those kinds of things, they respond to stress. How does this happen? Well, we're not entirely sure, but what appears is when bone gets stressed, okay, remember, what do you have a lot of in your bone? You have a lot of ions, right? Calcium, right? Calcium is a +2 or ++ ion, right? It loses 2 electrons. And you have some other, we call polyatomic ions, like phosphate in there. And these ions, because they're electrically charged, okay, when they kind of get moved around, they can produce an electrical field. And what we think happens is this electrical field that changes or gets produced attracts osteoblasts. So you stress that bone, and there's an electrical field that's produced, and that draws osteoblasts into that area, and then they start building up bone or osseous tissue in that area in response to that stress. And so there has been some research into bone healing and applying electrical fields and using electrical therapy to help people heal, like fractures and things like that. I don't know where all that research is at this point, but I know that there's some active investigation into this. So that appears to be the general mechanism behind bone remodeling. Now, is calcium a metal or a non-metal? It's a metal, right? It tends to lose electrons. And calcium is a metal. And there are some other metals that can have, at least as far as the cells are concerned, there are other metals that can kind of masquerade as calcium or kind of quote unquote look like calcium. Okay? And some of the important metals that you want to throw in the back of your mind are going to be metals like lead, uranium, plutonium, cobalt. Okay? Some of these real heavy metals. And why is this a problem? Well, let me ask you guys. Is there a problem with heavy metals masquerading as calcium? What do you guys think? What I mean by that are, will these cells, if you have a lot of this heavy metal in your body, will those cells think, okay, quote unquote, think that those heavy metals are calcium and then start incorporating those heavy metals into the matrix of the bones? Yes, they will. And this is a problem, right? Because this makes it really hard to get rid of those heavy metals, right? Which of these heavy metals is a particularly pressing problem right now, actually? We have a massive crisis going on in a certain area of our country involving one of these heavy metals. Huh? Lead. And where at?
Flint, Michigan.
Flint, Michigan, right? It's a suburb of what big city there? Detroit, right? A suburb of Detroit, Michigan. And there, the levels in the drinking water of lead are toxic. There are highly toxic levels of lead in the drinking water, right? Why is this a problem? Well, this is a problem because you drink the drinking water, the lead gets into your body, and then that lead can get incorporated into the matrix of your bone, and it'll be really hard to get rid of it, right? And it's even more critical if you had to imagine. Do you think this is going to be more critical in younger or older people? Why is it such a big problem in younger people? What's going on in younger people?
Their bones are developing.
They have lots of ossification occurring, don't they? They have lots of osteoblast activity. And so if there's lots of lead floating around in a little kiddo, okay, a lot of that lead can get incorporated in there, okay? And we know that lead is highly neurotoxic. It is toxic to the nerves. And you have lots of nervous development in your kiddos as well. And so there's a little mnemonic that I just kind of remember when it comes to lead toxicity. And this is not in your book, but it's just something I'll throw out. I just think of lead, L-E-A-D, and these are the warning signs of the major findings of lead. The first major finding is what we call lead lines. All right? And this is specific in kids. And what will happen is you'll take an x-ray of a kid, and those of you guys that are familiar with x-rays, when an x-ray is really white, that means what? What does a white x-ray mean? It's really white.
There's a build.
That means that what kind of tissue is so what is an x-ray? An x-ray is just a photograph. It's just a picture. That's really all it is, okay? So you take a photographic plate, okay? That's a plate that when it gets hit by light, it becomes dark, okay? That's what a photographic plate is. When light hits it, it becomes dark, right? Now, the kind of light that we use for an x-ray is not the kind of light that we can see. It's not the visible spectrum. It is a high energy type of light known as an x-ray, right? It has a very small wavelength, high energy. So if you take, say, a hand here, so let's say that I have a hand, all right? I take a hand and I put that hand in front of the plate, okay? And what did I tell you? I said if light hits the plate, what happens? The plate turns black, right? So if I put my hand in front of the plate, okay, and then I shoot x-rays, all right, so I shoot a bunch of x-rays here, all right, well, where my hand doesn't Where my hand is not blocking the plate, that area of the plate's going to be completely black, right? But where my hand is going to block some of those x-rays, right? And the more of those x-rays that get blocked, the less dark the plate is going to be, right? And so what we find is tissues that are very dense block more x-rays, and so your bones tend to be what color on x-rays? White. Does that make sense? And it is not because the x-rays are going through the bones, it's because the x-rays are being absorbed by the bones, right? And so that area of the photographic plate is not getting exposed. Does that make sense? That's what white, so dense tissue absorbs more x-rays. That means less x-rays are hitting that plate, making it dark, right? And so what we see is these really thick white lines that develop along the epiphyseal plate, right? Their growth plate in kids. And that's known as a lead line. You get lots of lead. Lead is a very heavy element. And it accumulates in there and makes these really thick lines on there.
But it also affects MRIs, doesn't it?
What's that?
The lead.
I don't know if lead. MRI is not an X-ray. It's very different. It works on.
It is. I worked for an MRI place.
Okay.
And I know one time.
I don't know.
A little boy had a lot of lead.
It could be. If see, lead is it's going to be an ion. It's going to be ionic. So it's probably going to have. Yeah. I don't know. I don't want to say something wrong, but anything magnetic is going to affect an MRI. And basically, when you have unpaired electrons in the valence, you are what we call ferromagnetic, and that's actually how MRI works. Is it excites hydrogen atoms in the body, and then they resonate, and when they go back, there's has something to do with something known as spin, electron spin, but they release radio waves that can be detected, but. Certainly, it could, yeah, it could. Certainly, large deposits of it could be a problem, or large deposits of iron is another big one. Sometimes people that are like metal workers, before they get an MRI, will x-ray them and make sure they don't have little pieces of metal in their eyes, because that can be a problem, yeah. So yeah, lead might be. So you got lead lines, all right. And then that's the L. The E is what we call encephalopathy. So pathy just means dysfunction or disease, and then encephalo is brain. So they have brain problems. They have cognitive, behavioral problems. Their brain doesn't function very well. Okay. So far, so good. So you have those lead lines that develop. You have this encephalopathy, or this kind of this brain dysfunction. Okay. You also develop anemia. Anemia and abdominal pain. And anemia means that you have a low level of what? Okay, iron, red blood cells, yeah. Okay. They become anemic. And then D is drop. Specifically something known as foot drop and wrist drop. And this is a neuromuscular dysfunction where you cannot activate, the neurons are not able to activate the muscles that are involved in your foot and wrist movement. And so what'll happen is you'll have, your feet will drop down and you won't be able to do this, or we call flex, right? You won't be able to flex your foot. You get that foot and drop. Sometimes you see that foot drop in people that have spinal injuries as well. They have compromise of the spinal nerves. So we see these in people that are severely lead poisoned. It's a big problem in kids because they're developing so much. Big problem in Flint. And where did all that lead come from? Yeah, the pipes. The pipes are made of lead. Yeah. And there are actually a lot of cities in the United States, very old cities, have very old infrastructure, lead pipes are very common because lead doesn't tend to corrode. It's a pretty robust element. Unfortunately, it does tend to leach out a little bit over time, and that can be problematic. It used to be, the big problem used to be paint. Paint used to contain lead. And houses that were painted, that had a lot of lead paint in them, were a big problem, particularly with kids. You get a lot of lead dust, and sometimes the kids would even eat paint chips. It could be problematic. But now, the big problem that we're running into is lead pipes. Right? So you imagine it's a big mess, and it's going to be a big, pretty expensive project to get that. Because what do they have to do? They have to replace all the pipes, right? Ultimately, to get that drinking water safe. Okay, you guys good with that? So far, so good? Okay, cool. Let's see here. So let's now talk about regulating our bone remodeling and to some extent ossification as well, and the major hormones involved. Okay, so these are 3 major hormones, and there are 2 more, but they're so special I'm going to talk about them separate. So the first one I'm going to talk about is something called calcitriol. Okay. Where does calcitriol come from? Where is it secreted with? This is the kidneys. Yeah, calcitriol, the kidneys. Now, calcitriol needs something to be produced, right? There's a vitamin that is essential for the production of calcitriol. And what is that vitamin? D. What type of D though?
3.
D3, right? Vitamin D3. Yeah, vitamin D3. Okay. Calcitriol is secreted by the kidneys, and what does calcitriol do? When it's secreted, what is its action? I think there's a nice table in your book that really just summarizes all this. What's that? Say it again? There we go. So calcium and phosphate absorption from where? From the GI tract, right? That enables us to absorb calcium and phosphate, which are primary components of the hydroxyapatite, right? Make sense? Okay, so that's calcitriol, okay? What about growth hormone, or GH? Where does that, what organ or what area secretes that? The pituitary gland, good. Don't worry, we're going to talk about the pituitary gland in some detail when we get into endocrinology. What does growth hormone activate? What cell primarily does it activate? Say it again? There we go. Yeah, the osteoblast. Blasts. Okay, and this is important because what do the blasts do? They build, right? They build. And where do we need lots of building? Well, we need it here, right? During ossification. So growth hormone is very important when it comes to the developing kiddo. Right? As the kid develops adult-like bones, right? The growth hormone actually does several things, but one of the things it does is it activates those osteoblasts that allows this hyaline cartilage to be replaced by bone, or allows for that endochondrial ossification. However, there are some diseases involving growth hormone. And I believe there are some case studies in your book, but we'll just briefly talk about them. Okay, one of the diseases is a disease of too much growth hormone. Okay, too much growth hormones being released. Okay, and what do you imagine will happen if you have too much growth hormone being secreted as your bones are growing? Yeah, you're going to have this over-exaggerated bone structure that develops. And what is a disease? Marfan syndrome is a connective tissue, which bone is, but it does not, Marfan syndrome isn't bone so much as it is cartilage and the connective tissue proper. And okay, gigantism, yeah. What is another name for that? Acromegaly, right? Acromegaly. And there's a little case study in your reading as well, right? Really tall guy, right? Really big guy there. Okay, so he's over-exaggerated bone development. Not only is this person tall, but has lots of bone tissue, right? And then you do have what's called Marfan Syndrome. But Marfan Syndrome is more to do with the connective tissues that hold your bones together, your tendons, your ligaments, right? And we talked about that in histology because it could make you more prone to like dislocations, can make your vessels more prone to developing aneurysms and rupturing and having sudden death. So that's your Marfan syndrome there. Yeah, so gigantism. You can also have something called Pituitary Dwarfism, which is what's going on there. Yeah, you're not producing enough growth hormone, right? So you have this dwarfism, okay, where you don't have enough bone growth occurring there. Okay, you guys good with that? Okay, and then we have sex hormones. Okay, and your sex hormones start being produced around puberty. Okay, that's what heralds the onset of puberty is your sex hormones. And what areas of the body do we see sex hormones being released? The testes and the ovaries, good. Testes and ovaries. All right, so you have your androgens, which are your male sex hormones. And then you have your female sex hormones, your estrogens. Okay. And yes, guys need a little bit of female hormone or estrogen as well, right? Okay. It's not a all or nothing kind of thing. It's just that you see more testosterone in men and less testosterone in women, and then you see more estrogen in women, less estrogen in men. But both estrogen, testosterone, and other sex hormones are present. But it's a little easier to kind of look at it as, okay, testosterone is more of a male thing, etc. Okay, testes and ovaries, you have these sex hormones. What do the sex hormones have to do with bone ossification? What's going on there?
Osteoblast activity.
Okay, and ultimately, what does that do? What do these sex hormones ultimately cause? And I believe it's outlined fairly nicely in that table in your book. It's that transition from kid bones to adult bones. What happens there? What's the, right? What kind of completes ossification, if you will? There you go. The epiphyseal plates close up, right? They close up, they harden. Good. Becomes a line, right? The plate becomes a line, and you have transition to adult bone structure. Okay, you guys good with that so far? So far, so good? All right, cool. Now what I want to do is I want to talk about two hormones, or two types of hormones, that are critical for regulating calcium levels in your blood plasma. Okay. Another term for blood plasma is what's known as blood serum. Okay. And where does this come from? Well, I think some of you guys are involved in drawing blood, right? Doing labs. Maybe in this class, work as medical technicians or technologists or CNA or no? Okay. I thought maybe some, yeah, draw blood. So what we do is we draw blood, okay, and you have it in a little tube. So here's a little tube, a test tube, okay. This is obviously enlarged a little bit because it's only a couple milliliters. And what we do is we take that blood, and remember, blood is a tissue, is a living tissue that has a mixture, right? It has the extracellular matrix, it has the white cells, the red cells, the thrombocytes, all the proteins, right? So what we do is we put that in what's called a centrifuge, okay? We put it in a centrifuge, and that spins the blood, around very fast. Okay, it produces a centripetal force. And that centripetal force causes the heavier elements of that blood to sink down to the bottom. Okay? So what happens is all the heavy stuff, the red blood cells and the white blood cells, okay, get pulled down to the bottom, okay? And then on top of them are the lighter elements in the blood. And what do you suppose the lightest part of your blood's going to be? Your plasma, yeah. And so when you spin blood down, okay, you'll see all the packed cells near the bottom, and then on top of that, you'll see kind of a yellowish, orangish, watery-looking substance, and that's the plasma. And what we do is to find out what somebody's plasma or serum level of, say, calcium is we would take a sample from the plasma and test the level in the plasma. Does that kind of make sense? Okay, so that's where that comes from. Calcium, as we will get to, we won't talk about any of the detail today, but calcium is critically important for neuromuscular transmission. Specifically, you need calcium for your muscles to contract. You cannot have muscular contraction without adequate levels of calcium. Okay? So you need to have a certain amount of calcium in your blood. Okay? The normal level of calcium, give or take a little bit, is about 8.5 to 11 milligrams per deciliter. That's the normal concentration of calcium. So 8.5 to 11 milligrams per deciliter. What's a deciliter? Deciliter. Going back to the orders of magnitude exercise in lab. Remember we talked about the metric system?
A tenth?
Not a tenth. 1/100th. Yeah, a deciliter is 100 milliliters, or 1/100th. Right? Or I guess it would be 1/10 of a liter, wouldn't it? A deciliter would be 1/10 of a liter.
I thought decament 10.
Yeah, you're right. Yeah, so it's 1/10 of a liter. Yeah, or 100 milliliters. 100 milliliters is 1/10 of a liter. So for every 100 milliliters, or every tenth of a liter of blood plasma, you should have dissolved in that 8.5 to 11 milligrams of calcium. Does that kind of make sense? Okay. Now, this is kind of different because the other electrolytes that we talked about were measured in milliequivalents per liter, right? Not milligrams per deciliter. So calcium's a little different in that. And there are actually different forms. There's ionized and non-ionized. We don't have to go into any of that detail. But less than 8.5 is what we call hypocalcemia. Hypocalcemia. Just like low potassium is hypokalemia, right? Low sodium is hyponatremia. Low potassium is hypocalcemia. High potassium is hypercalcemia. Okay, significantly greater than 11 milligrams per deciliter. How does our body maintain a balance between hyper and hypocalcemia? Well, there are two major hormones involved in that. And I want you guys to throw them at me. What are they? One comes from the thyroid gland, I'll tell you that, I'll give you a hint. One comes from the thyroid gland. Where does calcitonin come from? Cool. Calcitonin, okay, comes from the thyroid gland. What cell? What type of cell type? The C cells, good. Okay, the thyroid gland. And what does calcitonin do? It basically does three different things.
Regulates Osteoclast.
Say it again?
regulates Osteoclast.
Okay, so well, how does it make them work or keep them from
Slows
working?
them down.
Inhibits.
That's inhibit. There we go. Inhibit osteoclast, right? So it inhibits the cells that break bone down, right? So if you inhibit the cells that break bones down, that means that your bones are not releasing calcium, right? So it inhibits the release of calcium from your bones. Does that make sense? Where else does it work? Do something to the kidney?
Moves calcium.
It tells the kidneys to get rid of potassium or calcium ions, right? So increased loss of calcium via the kidney. So you pee off calcium, right? Okay, so you quit releasing it into your blood, you pee it off, and what else?
Reduce concentrations in body fluids.
And that ultimately leads to decreased levels in the plasma. So if your calcium level is getting too high, okay, your thyroid is going to release calcitonin, and that calcitonin is going to cause a decrease in calcium levels. You guys cool with that? But do we have something, what if our calcium levels are getting too low? Do we have another hormone that increases calcium level in the blood? Yes. And what is that called? What's the hormone called? PTH? Parathyroid hormone. All right. And that comes from the parathyroid gland. Where is the parathyroid gland? Yeah, it's actually along the sides. Right? Para means alongside, right? Like paramedic means alongside. Medic means doctor. So paramedic literally means alongside the doctor. So parathyroid is alongside the thyroid gland. And this inhibits what? Or enhances what? What does parathyroid hormone do to our osteoblasts and or osteoclasts? Stimulates the clasts, right? Good. So it stimulates the clasts. Okay, that causes them to release calcium from the bones. And what does it do to our kidney?
Increases the rate.
It decreases loss of, right? It increases retention. Okay, so decreases loss. And that ultimately does what? Increases our calcium levels. So it is this balance, this interplay between calcitonin and parathyroid hormone that helps keep our calcium levels nice and balanced out. Right? Prevents us from becoming hypo or hypercalcemic. Now there are some conditions that can result in calcium imbalance. One that we run into, anybody looking at becoming a nurse or work in a nursing environment, probably a lot of you. One situation that we run into is people that have thyroid surgery. Okay? In thyroid surgery, because the parathyroid glands are located alongside the thyroid gland, it is possible to remove them or to compromise them. And so people that have had thyroid surgery, particularly right after their surgery, they are going to be at risk for, specifically, they're going to be at risk for this here. Their parathyroids are compromised. That means that they will not be able to maintain adequate levels of calcium. They're going to be prone to hypocalcemia, life-threatening hypocalcemia. And there are two signs, and I do not believe this is talked about in the textbook, but I'll just throw these at you because they're so important. There are two assessments that we look at in people people that are at risk for hypocalcemia. okay? And I'm gonna put you on the spot, Ernie, because this is something you should know. All right, this is med block 2.
Oh, okay.
Paramedic school, med 2, man. What are those signs?
For hypocalcemia.
Life-threatening hypocalcemia. Yeah.
Life-threatening.
Something to do with the cheek, blood pressure cuffs.
Oh,
Say it. Say it. Say it.
You rub. You can.
Tap the cheek.
Yeah.
And what does that cause when you tap the cheek?
Like contraction.
There you go, yeah. So you'll tap the cheek, and what'll happen is you have muscular irritability when you become hypocalcemic. Your muscles get really irritable, and so you'll tap the cheek, and the side of their face will start spasming, and that's called the Shavastic sign. Shavastics. I just think of Shavastic cheek, right? Shavastic cheek. That's CHVOSTEK. Kind of a weird spelling there. CHVOSTEK. This is not in your book, so you know it's not something that. Right? So you tap the cheek, they have spasms. The other sign is known as the Trousseau sign. Trousseau sign, and that I believe that's TROUSSEAU, I believe is how that's spelled. Trousseau sign.
Spell it again.
TROUSSEAU, I believe is how it's spelled. All right. Probably should have looked it up, but I believe that's it. Okay, Trousseau sign. And Trousseau sign is when you put, you guys know what a blood pressure cuff is? You guys have all seen that. You put a blood pressure cuff on the arm, and as you inflate that blood pressure cuff up and it starts activating those nerves, what will happen is they'll start developing spasms. We call carpal spasms. Their hand will spasm up like that. So the Shavastic and the Trousseau sign, when you see that, you know that they might have life-threatening hypocalcemia, and we may actually need to give them calcium in the IV to stabilize their calcium levels. So that's a real-world application involving calcium imbalance that occasionally we run into. Okay, tell you guys what, let's get you out on a break, and then we will come back and we'll talk about fracture healing. We'll talk about osteoporosis, and then we'll talk about some terminology that we'll be using involving bones. But I'll take a good 10-minute break, and I'll see you guys in a few.